The last model that we're going to go over is molecular orbital theory. This theory gives us some advantages over valence bond in terms of it explains our magnetic properties of molecules better. So in molecular orbital theory, we are going to take atomic orbitals and blend them together to create molecular orbitals. So these are now orbitals shared by the molecule, not just orbitals carried by an atom. So what happens when we take two atomic orbitals, or however many orbitals that we're blending together from two atoms, we're going to get out the same number of orbitals as we put in. So if we start off with two atomic orbitals, we're going to create two molecular orbitals. And the average is going to be the same as the average of the atomic orbitals. So for us to make a bonding situation, one of these orbitals has to be lower energy than the atomic orbitals. If it's not lower energy than the atomic orbitals, then we cannot form a stable bond. But if one of these orbitals is going to be lower energy, the other orbital has to be higher energy. So when we take two atomic orbitals, we blend them together, and we're doing a process called a linear combination of atomic orbitals. This will give us a low energy bonding orbital and a high energy anti-bonding orbital. So when we blend together two orbitals, two atomic orbitals, we're going to get two molecular orbitals, one bonding, one anti-bonding. Filling up both the bonding and anti-bonding, the molecule will have zero energy, meaning that it is not connected and it will fall apart. So this is an example of how we can get molecular orbitals from atomic orbitals. So we're doing a linear combination of atomic orbitals. So if we blend together two s atomic orbitals, we're going to create a lower energy bonding orbital and a higher energy anti-bonding orbital. What we're going to do is for our sigma bonds, not our pi bonds, so we're going to have two types of bonds, sigma or pi. Sigma is when the electron density is on the bond axis, and pi is when it is above and below the bond axis. So this is a sigma bond, so we're going to label this sigma. If we can identify the atomic orbitals it comes from, we're going to use that designation. So this is coming from two 2s orbitals, so we're going to create a sigma 2s molecular orbital. This is the bonding orbital, it's lower energy. The anti-bonding orbital we're going to represent with an asterisk. So we have a sigma asterisk 2s. So these orbitals, the way they look is that the bonding orbital consists of two 2s orbitals of the same sign. So the electrons overlap and add together and create a large cloud that encompasses the two nuclei and fills the space between the two nuclei. So that is our bonding orbital. The anti-bonding orbital will contain two 2s orbitals of opposite sign. Since they are opposite sign, they cannot overlap. So there's going to be empty space or node between them. That means the space between the two nuclei is mostly empty of electrons. So this does not hold the atoms together. So this is an anti-bonding orbital. So it will have a node covering the space between the two atoms. So we're always going to get a bonding orbital and an anti-bonding orbital out when we blend together two atomic orbitals. So on the p level, so over here, this is showing how we blend together the atomic orbitals to create the molecular orbitals in the middle. So the 2s blending together to form a sigma 2s and a sigma asterisk 2s We showed that in the last slide. Now we're showing the 2p blending together, where we're going to have 3 2p orbitals from each atom. That's a total of 6 atomic orbitals, so we're going to create a total of 6 molecular orbitals also. So for most elements, when we blend them together, the sigma is going to be the most stable. So that would be this version down here where the 2 p orbitals are lined up with the bond axis. The center 2 lobes are the same phase for the electron, so they can overlap, and we have a lot of density between the 2 atoms, and that creates a stable bond. When the 2 meeting lobes are opposite phase, they cannot overlap. There's going to be an empty space node between them. This is an antibonding. This is high energy. So the sigma bond tends to be the lowest energy molecular orbital, and the sigma antibond is going to be the highest energy molecular orbital. Now we're going to have 2 sets of p orbitals that are parallel to each other and above and below the bond axis. So when we blend these together to create a molecular orbital, the bonding one is when it's the same phase above and below the axis, so we get a big lobe between the 2 atoms, but it's going to be above and below the bond axis. So that is our pi bond, our stable pi bond. There's going to be 2 sets of those, so we designate that as pi 2p to represent the 2p's to represent the atomic orbitals that create this stable bonding orbital. When they are opposite phase above and below, then there's going to be a node, an empty space in between the 2 atoms. And this is our antibonding pi orbital. So again, the electron density is still above and below the bond axis. That's our bond, our pi bond. But there's a node in between the atoms, so that is our anti-bond. So that gives us our 2 pi asterisk 2p. So our 3p levels will generally create the lowest energy 6 sigma 2p, the next 2 equal energy pi 2p's, then 2 equal energy antibonding pi 2p's, and then the highest energy antibonding sigma. We do have 3 elements where the rearrangement of this level is, the bonding levels is switched, and that's for boron, carbon, and nitrogen. That in those cases, some hindrance between the orbitals raises the energy of the sigma above that of pi, so the 2 pi orbitals are lower energy than the 1 sigma. So we use as much of this blending as we need to describe. We generally are only describing the valence electron, so we don't need to show 1s if we're on period 2. If we only have s electrons, then we just need the bottom portion of this chart with a 2s blending to form the sigma 2s and sigma antibonding 2s. And then if we have p electrons, then we're going to blend the 2p together. And if we have oxygen or larger elements, then the sigma is going to be the sigma 2p will be the lowest energy, pi 2p will be next, and then the pi antibonding and the sigma antibonding. For boron, carbon, and nitrogen, there is a repulsion that raises the energy of the sigma 2p. So the pi 2p becomes more stable than the sigma 2p. So that's for boron, carbon, and nitrogen diatomic molecules. So we just have a little rearrangement of our stable sigma and pi levels for 2p. So we're going to use these orbitals to create and describe diatomic molecules, primarily homonuclear diatomic molecules. Now that we have these diagrams, these energy level diagrams, what we do is that we fill them with the available electrons. So we're going to be working primarily with homonuclear diatomic molecules. So that's a diatomic molecule of the same atom, carbon 2, boron 2, oxygen 2, fluorine 2. We can have charges on them with negative charges, positive charges. So using the number of electrons that the two atoms have, we're going to fill these molecular orbitals from lowest energy to highest energy using the same rules for filling. So we're going to fill the equal energy ones with parallel spin single electrons before we pair them up. And then after we fill them with available electrons, then we can determine the bond order and whether the molecule is paramagnetic or diamagnetic. For heteronuclear diatomic molecules, these are more difficult to describe because the atomic energy levels do not match. So they come in at different energies, and we need a little bit more processing power to determine the levels of both the atomic and the molecular orbitals. So this diagram on the right is showing how a heteronuclear one looks like. So our 1s energy level for the hydrogen atom is a higher energy than the 2p energy level on the fluorine. They don't match. They're going to create one bonding orbital, bonding molecular orbital, and then one anti-bonding molecular orbital. So we use some additional computing power to be able to calculate the relative energy levels of both the atoms and the molecules. So for bonding order, what we're looking for is pairs of bonding electrons, subtracting off any anti-bonding pairs also. So pairs means that for our bond order, we're going to divide number of electrons by 1/2 to get a pair. We're going to take the total number of bonding electrons minus the total number of anti-bonding electrons to get the number of bonding electrons divided by 1/2, and that'll be our net number of bonds that we have. So if our bond order comes out to be 0, it's no bond, the molecule will fall apart. Our bond order can be fractional from 1/2, 1, 3/2, 2, 5/2, 3, and etc. So fractional bond orders are acceptable. So if we have a positive bond order, we have a stable molecule. A 0 bond order would not be stable and would fall apart. So to count them, we have to just recognize our molecular orbitals, which ones are bonding. So we're going to have a bonding molecular orbital here. The next one above this is the anti-bonding sigma 2s. So if we have a pair in the bonding, pair in the anti-bonding, this is a total wash. This does not hold the molecules together. And we keep looking up. So if we have a pair in the pi level, this creates a bonding effect here. So our bond order, we count the number of bonding ones. So we have 2, 4 bonding. We have 2 anti-bonding. So we do 4 minus 2 give us 2 bonding electrons. Divide by 2, and that means we have 1 bond available. For the HF molecule, we have 1 pair on the bonding level. So we have 2 electrons divided by 2, and we have 1 bond order of 1. So bond orders, we increase our bond order. If we have bond order of 0, we have no bond. It just falls apart. It's not stable. As we increase bond order, our bond is going to start long and then get short. And as we increase bond order, we're going to start off with a weak long bond and become a strong short bond. For conjugate double bonds where they're separated by a single bond, classic example of this would be a 1,3-buta, which is 4 carbons, di-2-ene, 2 double bonds. So it's a butyl molecule containing 4 carbons with 2 double bonds separated by a single bond. So if we have these 4 atomic p orbitals that we're blending together, we're going to get out 4 molecular orbitals. So the number of orbitals goes in is the number of orbitals that come out. So we're putting in 4 p orbitals. We're going to get 4 molecular orbitals out of it. So the most stable of this would be when we have all the signs be identical above and below the molecule. What this is actually saying is that we have one orbital that covers all 4 molecules that is both above and below the axis of the molecule. So that means that orbital can hold 2 electrons, a pair of electrons, and those pair of electrons will be moving over the whole molecule. The next bonding one, higher energy, the next bonding one, would be when a pair of pi orbitals are matching on the 1 carbon double bond and has a different match on the other carbon double bond. So that means on the single bond between, there is a node, empty space node of electrons. So now we're going to have a orbital, single orbital that has a node above this double bond and below that double bond, and above the other double bond and below the other double bond. This molecular orbital will take a pair of electrons that will be over the whole molecule, but occupying 4 different spaces in that molecule. So if we blend together 4 atomic orbitals, we're going to get out 4 molecular orbitals. 2 of them will be bonding, 2 will be antibonding. So these 2 were the 2 bonding molecular orbitals. And for this molecule here, we're going to have 4 electrons, one from each of the pi p orbitals. So those 4 electrons are going to occupy these 2 bonding levels. So this molecular orbital is also referred to as the highest occupied molecular orbital. The next one above it is the lowest unoccupied molecular orbital. So it's between these 2 orbitals that we have the most movement of electrons when we excite electrons. And on this molecular orbital, which is now an antibonding orbital, we're going to have a node between these 2 atoms across the double bond, another node across this double bond, and then the single bond will have a overlap above and below this. So the single bond will have a double bond on it. So this is a high energy orbital, not having any connection across these double bonds and having a connection across this single bond, the middle bond. And the highest energy molecular orbital is this one up here, where every carbon has a different phase on its p orbital. So there's no overlap across any of the bonds. All the bonds are unbonding, antibonding. So this is our highest energy antibonding orbital. So another property is the magnetism of compounds. A paramagnetic compound is attracted by magnetic fields. This happens when we have unpaired electrons. So that makes this molecule to be magnetic when it has unpaired electrons, because each unpaired electron has a magnetic field associated with it. Pairing electrons gets rid of the magnetic field. So unpaired electrons gives a magnetic field, which makes the compound paramagnetic. If we only have paired electrons, there is no magnetic field to that molecule. The lack of a magnetic field in the molecule actually makes it slightly repulsive to magnetic fields. So for the hydrogen fluoride molecule, we have only paired electrons, one pair of electrons, so all our electrons are paired up. This means no magnetic field. This means it means diamagnetic, which means slightly repulsive to magnetic fields. Whereas for the boron 2 molecule, each molecule has 3 valence electrons. We've put them here. We use a 2 pair for the bonding sigma 2s and the antibonding sigma 2s. For boron, along with carbon and nitrogen, the pi levels are lower energy than the sigma levels. So that third pair of electrons is going to go into a pi level. That means we'll have one electron in each orbital, single and unpaired. So we have 2 unpaired electrons. So the B2 molecule will be paramagnetic. That would mean that it would be pulled into a magnetic field. And we are complete with this chapter.